I'm Dan Dunkevich. Welcome to The Briefing. Today, we're going to continue our series on AI by getting into the hardware with answers to questions like, what's a GPU? And what's this I hear about NVIDIA being the most important company in the world? So let's jump right in. So all of this takes place inside of an AI data center, sometimes called an AI factory. That latter term is pretty much an NVIDIA marketing term, and it can be used interchangeably with AI data center. So let's talk about what goes on inside there and what the components are. First, there's the CPU, or Central Processing Unit. Now, CPU is often known as a chip. That's the thing that's in your laptop. It's in the camera I'm talking to right now. It's in my phone and everywhere else. So many different kinds of CPUs. Some have a small number of cores, or one core, some have 5 or 6. But the idea of a CPU is it's a general purpose computing device. And these have been around for a long time. And they have a small number of cores, but they're very complex because they're very versatile. They can do many things. They tend to process in a serial manner. So I do this action, then this, then this, then this. They have some degree of parallelism, but that's not their primary raison d'etre. And in an AI context, they are used as the system manager. So they control the memory usage, they control jobs, and decide which cores get what work to be done. Now, Intel provides about 50 to 70% of the CPUs in most data centers. AMD is another large player, and NVIDIA is trying to catch up into that as well. This moves us on to the big one, the GPU, the Graphical Processing Unit. Now, this particular device was also very old, like the CPU, and is used, as you could guess, to process graphics. So when you look at a screen, you probably have millions of pixels on the screen. But these millions of pixels aren't doing a whole heck of a lot. They're either turning on, they're off, they're red, they're green, they're blue. Not a lot. And so a GPU has many, many simple cores, thousands of them, to manage all of these pixels. So they're all built around being a hyper-parallel architecture that can do a lot of simple things in parallel, which makes them very perfect for neural nets, which is where we're getting to next. In 1998, Ian Buck at Stanford developed a language and then used that language to train neural networks and put them on top of a GPU. And this was called AlexNet. And this showed that GPUs and deep learning neural nets are the way forward for all of AI. AI research had been going on for a long time, but really hadn't been making as much progress as you might hope until this breakthrough. In a lot of ways, this was the iPhone moment for AI. And so from there, we got our ChatGPT, self-driving cars, and all those kinds of things. But that took some time to fully develop. Now, AlexNet ran on 2 NVIDIA GPUs and was capable of performance of 0.5 petaflops. A flop is a floating operation. And that's basically a simple mathematical computation that it'll do, and it's a good measurement of the power of such a chip. So 0.5 petaflops, that means 0.5 times 10 to the 15. So it's basically a 5 with 14 zeros after it. Now in 2022, ChatGPT exploded onto the stage, and it was powered by 20,000 NVIDIA GPUs, newer ones, A100s. And this thing used 80 petaflops of performance. It's 160 times faster. So this is the sort of growth you see. And that was 2022. Now in 2024, just 2 years later, xAI built Colossus. And this is what runs the competitor to ChatGPT, which is called Grok, G-R-O-K. Now, Colossus was originally built with 100,000 NVIDIA H100 GPUs. It's now up to 200,000 of these GPUs. And it's 2 million times the power of AlexNet at 1 exaflop. That's kind of a funny name. But that's a 1 with 18 zeros after it, how many computations it can do. And by 2026, xAI plans to expand this rig up to 1 million GPUs. That's 10x in 2 years. So, GPUs, massive expansion, and they account for 50 to 60% of the total spend on building an AI data center or AI factory. And NVIDIA accounts for about 90% of that market. AMD has a challenge to it, but they're quite a bit behind. Same with Huawei. They're also behind, but they are working very hard to catch up. So NVIDIA, although they have 90% of the market now, they won't forever. They're pretty much at their peak. That doesn't mean that they won't have greater sales in the future, but there's no way you hold on to 90% of a market forever. So let's move on to the next device, a TPU. This is a tensor processing unit. In 2016, Google invented this idea to do a very efficient way of processing matrix math operations, which is really the core of what an AI inference engine needs. And Google deploys them extensively in their infrastructure running Google's AI known as Gemini, which you get every time you do a search. And they're also beginning to offer on other hyperscalers like Meta. TPU performance on certain tasks can be 10 times faster than a GPU at lower energy costs as well. We're going to talk about energy later. Downside is they're limited in flexibility. So you see a CPU is very flexible, but not as fast. A GPU is less flexible, but a lot faster, and a TPU is more specific and faster, less flexible. So the next step of this was the language processing unit. Now the LPU, this was introduced by a new company called Groq. Different Groq, this is G-R-O-Q, sorry for the confusion. But it was founded by Google's TPU inventor, a genius named Jonathan Ross. This was founded right in 2016. So right after they got the GPU out the door, Ross left and founded his own company to focus on much more specific language processing, which takes the ideas of TPU and focuses them so that you can do certain language operations even faster as well. Now, NVIDIA realized the importance of this, and they just recently, about a month ago, entered into a $20 billion non-exclusive licensing agreement. And when you look at it, it looks kind of like a buyout because they get the IP and they get key people, including Jonathan Ross, now works at NVIDIA, but it's not actually a buyout. Now, you're probably going to see more deals like this going on in the future, particularly when you're dealing with very large companies, because a deal like this, as opposed to an acquisition, doesn't have to get regulatory approval. So you're basically just licensing it and getting some of the people. But it's not exclusive, so it's not quite as useful to a company as a buyout would be. However, it gets to happen very, very rapidly. And in this market, speed is more important than anything else. So looking at all of these devices, the CPU, the GPU, the TPU, the LPU, what's the future? Well, the future isn't going to be one of these items replacing it. It's going to continue to be a suite of these capabilities put together, with CPUs continuing to run the show and the other processing units doing what they do best. So this is just going to continue growing. Now I'm going to step away from hardware for a moment and talk about a thing called a token, because you'll hear about this, that these AI systems are basically just generating tokens. So what's a token? Well, a token is a chunk of text that the AI uses as its basic input-output, its basic computational atom, if you will. Now that usually would be like a syllable, or maybe a multisyllabic word if it's one thing, like say the word simple. It's 2 syllables, but it's one thing. That might be 1 token. So in like unbelievable might be 3. Unbelieve able. So 3 tokens for unbelievable. And so this is how you manage what's going in and what's going out, because you're taking in text. These AIs are reading everything in the world. And then you put a query in text, it breaks that down into tokens and does math around that. And that's really what you're paying for as a user. Now the cost of these tokens is highly variable now. Could be 15,000 up to 120,000 tokens for $1. Now that doesn't mean that it's 15,000 queries. When you ask a query and you see your little AI with all these websites, 75 websites searched, well, those are all the tokens that it's using up along the way. Now that's being the big driver of everything. AI hardware and software teams are trying to find ways to make more tokens per kilowatt hour, because the power cost, that's what really drives the cost of AI, outside of course, building the factory to begin with. So it's the largest direct cost for a search right now. So the cost per token is likely to go down because the energy per token will be going down as the companies get better at doing this with new hardware and also new software. We'll talk about that in a later episode. We're going to have episodes solely about power because it's such a big deal. Now, Let's move back to hardware. Memory. Massive data, you need massive amounts of memory. Now, NVIDIA is pretty dominant with their architecture. It's called high bandwidth memory, or HBM. You'll hear about that. And that's where they put the memory right on top of the GPU and get it very close to it so it doesn't have to go through the system all the time. And obviously, whoever provides that memory makes a great deal of money. Micron made billions last year selling all this memory. Give you an idea about size. AlexNet, remember that? That was based on 2 older GPUs that had roughly 6 gigabytes of memory, which is quite a bit less than the computer that I'm going to be recording this into. Colossus, however, uses 16 million gigabytes. So that's, well, it's like 16 million computers. That's how much you're talking about here. Now, the leaders in this area are a company called SK Hynix, Samsung, and Micron. They're the ones that are leading in terms of memory. Next thing. Network. You got all these GPUs and CPUs and all these racks, you got to talk to each other. So you have 2 basic technologies here. You have InfiniBand, that's been a long-standing leader, and you have high-speed Ethernet. Now, high-speed Ethernet has some tricks of its own. It has remote direct memory access that allows direct memory-to-memory data transfers between GPUs without having to go to a CPU. So GPU to GPU without having to go up and then back down. So that makes it pretty quick. Both are about 400 gigabits a second with 2 microseconds of latency. So very, very high speed stuff. Now, who makes these network systems? NVIDIA again, Broadcom, Cisco, Arista, and there are some other companies as well. Now, you take all of these little components and you put them together into the building. Now, the building block of the building would be the reference rack. NVIDIA's reference rack has 4 servers in. So think of a rack, 2 feet wide and 6 feet high. So 4 servers. Each server has 2 CPUs, 8 GPUs, 30 terabytes of storage, and 4 networks. So you have 4 of these inside of each rack. Each rack can consume up to, catch this, 50,000 watts. 50,000 watts is 5 to 10 times a single-family home, all going through this small little area. So you think about this for a moment. You think about, wow, you take an area that big and put 50,000 watts through it. Think of the density of power cabling, data cabling, coolant hoses, and they use air and liquid cooling systems to do this. You put that much power, you have to use liquid cooling. You have to blow a fan on it. So you got cooling hoses and control systems and hazards at these very, very high voltages and currents. So this is what makes out a data center. Very complex and astonishing how fast they get built. And we'll be talking about that in some future episodes. And that's today's briefing.